Hey guys, this is Mr. Marchman coming to you from sort of this dungeon-looking place of my top of my house. Um, so I'm not sure if I'm going to be with you guys this week, so I'm going to go ahead and give you guys a little video lecture or sort of a walkthrough of these AP practice problems. So hopefully you can, if you have questions, these will clear some things up. Okay, I'm going to take away the video because I look a little bit crazy here. So. Um, Maybe I can. Okay, there you go. So what I want to do is I want to look at these momentum and impulse problems and talk about sort of how to go through and solve them if you're having some trouble. I gave you some multiple choice, and I also gave you a couple of free responses. Depending on how long this video goes, I might just go through the multiple choice. We'll see. So the first one is, first of all, whenever you're looking um, at a momentum problem, or really any multiple choice problem in which you see a force time graph, you're thinking, oh, I've got to be thinking about finding the area to find the impulse. The area under a force time graph gives you the impulse. The impulse provided by whatever force we're talking about there. If this were a force displacement graph, the area would then tell us the work, and we'd be thinking about changes in energy. Here, we're looking at impulse, so we're thinking about changes in momentum. So let's think about this. What was it asking? It says a spacecraft of mass 4,000 kilograms is traveling in a straight line in the positive direction. So traveling in the positive direction, the engines can be fired so that the force exerted on the spacecraft is in the positive or the negative direction. You can see the forces up here are positive direction and the force in the negative direction. Which of the following is the best estimate for the net change in speed of the aircraft from time 0 to time 4? So remember, change in momentum is mass times change in velocity. So I'm looking for this change in speed from 0 to 4 seconds. So that's right, I'm going to be trying to find the impulse here. And once I get the impulse, I can divide by 4,000 to give me the change in speed or the change in velocity. Okay, so this is pretty typical of an AP problem where they're not going to give you a straight line with nice pretty shapes. They're going to give you a more realistic data collection going on here. And so what you're going to need to do is think about, okay, what sorts of what shape does this look like? To me, this looks almost like a triangle, and then it sort of is 0, and then I would say it sort of drops down to a sort of almost linear down here, or rectangular shape here. And so what I'm going to try to do is I'm going to try to find the area of this section and then subtract the area of this section since it's below the x-axis, and that will help me find the impulse. So let's find that change in momentum. The change in momentum is 1/2 of, this is the base, which is 2, times the height, which is 1,000, plus 0, plus the base, which is 1, times the height, which is -500. And so when I get there, I get a change in momentum is equal to 1,000 minus 500, which is 500. And what I'm going to do then is I'm going to take the impulse, and I'm going to, so this is again the change in momentum, kilogram meter per second. I'm going to set this equal to mass times change in velocity. We know the mass is 4,000, so I just simply divide by 4,000, and that gives me 0.125. Is this a positive 0.1 or a negative 0.1? Did my speed increase by 0.1 or did it decrease by 0.1? Well, that all depends. It depends on the direction that the impulse, well, in this case, the direction that the impulse is in the positive direction. You can see that the amount of force in the positive direction, the impulse in the positive direction is greater than the impulse in the negative direction. And since it's traveling in the positive direction to start, right? Traveling in the positive direction to start, and it incurs a positive impulse, then it has a positive change in speed. Okay? Let's look at the next one. Here we have two blocks connected to opposite ends of a compressed spring. The blocks initially slide together on a frictionless surface with a velocity v to the right. I want to do a couple things here. Maybe I want to delete that. I don't like that. So let's see if I can draw a line here. I'm not sure why it has a arrow on it. That's fine. We got two boxes. Sorry, can I make that bigger? There we go. And we have a compressed spring between them. So it's compressed. It's holding these two things together. And we know a couple things. We know that these two are moving to the right with velocity v. So again, these two boxes they're identical boxes. So let's just call them M and M. That'll make it easy. They initially slide together to the right. So we can say that the initial momentum of the system, right, is M times V. So we know that if there's no outside forces, no friction, nothing coming in, no outside impulses, that the final momentum of the system must also be mv. That's huge. Okay, just because if they weren't moving, the final momentum would be zero, and the initial momentum would be zero. But here, because they're moving, because they're both moving at the same speed, right? They're stuck together. They're moving to the right with some speed v. They have initial momentum. The spring is then released by remote control. At some instant later, the left block is moving at v/2 to the left. So this block begins to move. So at v/2 to the left. Remember, these are identical blocks. And the other block is moving to the right. We don't know how fast it's moving, but it's moving to the right. At some speed. What is the speed of the center of... Oh, interesting. Okay, so what is the speed of the center of mass of the system at that instant? Now, this is a little tricky problem because they're trying to sneak something in here. They're trying to figure out if you understand what it means, what this term means, center of mass. The only time that an object's center of mass will accelerate, in other words, will change its motion, is if there is a force acting on the object's center of mass, an outside force. You remember Newton's second law says that objects accelerate if there is a net force divided by, accelerate according to the net force divided by the mass. This really is described as the acceleration of an object's center of mass is equal to net force divided by mass. So if there is no net force on this center of mass, which there is not, there's no outside forces on this system, then the center of mass will not accelerate. So what is the speed of the center of mass? Hey, that's easy. That's v. So don't get tripped up and try to think about, oh, what's the speed of this block? They're only asking what is the speed of the center of mass. That's a very common momentum type question or center of mass question there. Okay, so let's look at this next one. This next one's a multiple correct question. So there's going to be 2 correct answers out of these 4. So I've got an object of mass 2 traveling to the right, and I always like to draw these out as I'm reading it. It's traveling to the right at 3 meters per second, and we've got some object B traveling to the left at 3 meters per second. And afterwards, so they collide, and afterwards, each has a speed of 3. Which of the following could be the mass of object B? Okay, so this is an interesting one. This is a little bit of a tough problem that I actually didn't really approach this mathematically. I sort of thought about, what are my examples here? For instance, could object B have a mass of 3? Could it? Let's take a look. If it had a mass of 3 and they collided, you can sort of do this process of elimination. If they collided, the initial momentum of the system, we'd have 6 to the right, we'd have 9 to the left, so the initial momentum would be -3, right? And you can fill in your units if you'd like. The final momentum must also be -3. So if B, right, well, first of all, B would have more momentum, right? So let's say it can, could it keep moving at 3? If it moves backward at 3, 2, so in other words, the final momentum must also be -3, right? Well, if B was moving this way at 3, then 2 would need to be moving much faster than 3 in order for that to occur. And if B were moving left at 3, then the momentum would be -9. 2 would need to be moving this way to the right really fast. So 3 doesn't look like it's a very viable option. What about 2? So if B had a mass of 2, the initial momentum of the system would be 0. Well, we have two choices for the final momentum to be 0. If the final momentum is 0, then they both stop, which that doesn't work because they both need to be moving at 3. So if they bounce off perfectly and 2 moves this way at 3, then hey, 2 would work. 2 might work. 2 would definitely work. Now let's skip down to D, negligible compared to 2, to the 2 kilograms. So let's say we have some tiny little dust fleck. Let's say B is just some little piece of dust that's moving this way at 3 meters per second. If it hits this box here that's moving to the right at 3, it's going to basically not affect this very much at all, right? It's not going to affect the 2 kilogram box at all. In fact, it says it's negligible compared to that. So it doesn't have very much momentum at all. So we can say the initial momentum of the system is approximately 6, which means the final momentum of the system is going to be approximately 6. Well, if 2 doesn't slow down very much, and it's going still pretty close to 3, that means this thing is going to be going pretty close to 3 as well, if it sticks to it. So the answer here is B and D. Those are your two best choices. And you can do the same reasoning for 1 and 3 as to why those might not work, or definitely will not work. Okay. All right, let's look at one of these free responses. This is a great free response. This is I forget which exam this is from. This is a good one. 7 points, suggested time 13 minutes. Let's see if I can get it done faster. I'm not going to go through the whole thing point for point. I'm probably just going to jot down some notes, stuff that you need to think about as you go through this. So here we have 2 blocks, A and B, of equal mass. It's always important to think about those things. There's a reason they put those things in there. On a frictionless track, and I like to sometimes underline things that are important to me. Block A, initially moving with speed v1, has a perfectly elastic collision. Perfectly elastic collision with block B. Perfectly elastic, remember, means not only is this true, initial momentum equals final momentum, but the kinetic energy is also conserved. All right, in a perfectly elastic collision. Block B has a speed v1 immediately after the collision and then travels around a circular loop of radius r, where r is much larger than the side of the blocks. The speed of block B at the top of the loop is v top. It then slides up the ramp until it momentarily comes to rest at some height h. Okay, so I want to derive an equation for the height h in terms of these 4 variables. So a perfectly elastic collision means that momentum is conserved. So if A hits B and then B begins moving at this speed, that means A must stop. Okay, so what do we know? Well, we want to derive an equation for the height h in terms of all these numbers. Well, this sounds like a conservation of energy equation to me. So we know that B, so the initial energy in the system plus the work done by non-conservative forces equals the final energy in the system. I'm going to go ahead and just write that out. That's my conservation of energy equation. Well, what's the initial energy in the system? Well, I can say that B has kinetic energy. It has kinetic energy of 1/2 its mass times V1 squared. And that's right here at this point here. It's going to go through this loop, and it's going to enter. It's going to go up the ramp. So I'm going to sort of skip this whole circular part and just focus on the energy at the very top here. So the energy when it gets to this height h up there. So at that height h, it's going to have mass. It's going to have all potential energy as it comes to a stop. And so now I can solve this. But notice when I solve this, I'm going to get some VI squared, aren't I? I can't have VI in my answer. So I have to think about something else here. Notice that I can use R. And here's R. Notice that the height at this point here is equal to 2R. So let me write out this equation again like this. Let's look at the energy here, and then we'll look at the energy here. Well, we know that the energy in each one of those spaces is going to be equal. So in this loop, this block has energy equal to, as kinetic energy equal to 1/2 m v top squared, but it also has kinetic energy because it's off the ground. It has kinetic energy due to its height, which is mg times its height, which is 2r. And then we also know that it has energy when it reaches the top of the ramp that is all gravitational potential energy. The block Earth system has gravitational potential energy there, equal to mg h. So here we go. This isn't going to be very useful to me, simply because I can't use this V1 squared, but I can use this stuff here. So I'm going to go ahead and just solve for h here. Notice that my m's don't matter; they cancel, and so I end up with h equals. Let's see what I end up getting here. 2r. I'm going to divide by g, so I get 2r plus v top squared all over 2g. You may have it written a little bit differently, but you should get something in that realm there. Now the second part says, suppose that the speed of block A is doubled. Will the final height of block B be greater than, less than, or equal to 2h? Interesting. So this is another energy type question here. If the speed is doubled and we still undergo that perfectly elastic collision, that means the speed of block B will also be doubled because kinetic energy is conserved. I can go ahead and tell you that it will be greater than 2h, but let's pretend we maybe don't know that yet. Let's explain how we got there. Well, if we look at this this equation for h, right? If I double this initial thing here, right? This initial speed, then I'm going to essentially quadruple the kinetic energy there, right? And so let's look at where that comes from. 1/2 mvi squared equals mgh. And if I look at this relationship here, by doubling this initial speed, I essentially quadruple my height, keeping all things equal. So all you really need to do here is you would need to explain that, but this would be sort of the basis of your evidence, your reasoning here. You can explain how there's this a squared relationship between height and initial speed. All right, let's look at this last part, and then we'll call it a day. We've got two blocks. They're moved to a different frictionless track, the same two blocks. Let VA be the minimum initial speed for block A that allows block B to make it over the hump in the track. Block A is then replaced with a larger block C, which has a mass 2m shown below, so double the mass. Block C makes a completely inelastic collision meaning they stick together, with block B so that both blocks stick together and travel along the track. What is the minimum initial speed VC that block C must have so that the two blocks doesn't make it over the hump? Express your answer in terms of VA. Interesting. Okay, so let's look at this here. Here we know we have MVA. We know that B is moving at VA to get over the hump, right? If it collides if A collides with B, B will then begin moving at VA, and it will barely make it over a hump. So we know that the minimum speed to get over the hump is VA, right? Okay, so let's take a look at what what's happening here. Let's set up a conservation of energy equation. The conservation of energy equation gives us this. We have 2m VC, that's the initial momentum of this big block here, equals the final momentum, or the momentum after they collide, which is 2m plus m times v. I'll call it VBC. That's the speed of these two blocks together. And so, solving for this, we get, or simplifying a little bit, we get 2mVC equals 3mVBC. Notice the masses don't matter. And so I get let's see. We need this speed, this VBC, we need that to equal VA. All right. So in order for it to barely make it over the ramp. So let's just substitute in for VA. So VC must equal 3/2 VA. Okay. So I hope this helps. I'll make another shorter video of the last two. Hopefully will help get you along the right track. Please let me know if you have any questions. You can reach me through email or anything like that. Good luck.